Hi everyone, welcome to this webinar about design for additive manufacturing. In this webinar I will explain you a little bit more on how to design for this technology and some important things to take into account during this design process. Additive manufacturing, 3D printing are two words which are often used for the same technology. For us, there is quite a difference between both. If we look at 3D printing, we can see that if it comes in the media or in the news, we see that people print clothes, print organs, print food, even print houses. But actually, those are not the kind of applications we are looking at. Those applications we prefer to call additive manufacturing. We use this technology, for example, to print high-end industrial parts. For example, hearing aids are printed with additive manufacturing, or all kind of other applications. Now, what's the difference between additive and other technologies? If we look at subtractive technologies, like turning or milling, we always start from a block of material, of raw material, and we remove material where needed. So we will have more geometrical restrictions. We will need a lot of different operations to remove the material. We will have a lot of waste during this process. And the more material we remove, the more expensive it will get. Now, if we look at, for example, cast technologies like injection molding, we often need very expensive molds. We need a lot of iterations to optimize this mold. The mold is often quite expensive, so we will need a high amount of parts to make it affordable. Now, if we look at additive manufacturing, because we start off a powder or a liquid material and we print only the material we need, we have a lot of geometrical and design freedom. We don't need any tooling. And compared to the other technologies, the more material we will print or use, the more expensive it will get. Now, if we look at the AM machine, I always like to compare it to the replicator out of the Star Trek movies. Actually, the replicator is a machine which can make anything you want, but the only thing they ask to the machine is Earl Grey tea, hot. And actually, it's quite similar with the AM machine. If you ask the same parts or the same applications to an AM machine as you do to a milling or an injection molding machine, you won't be successful with it. So you need to ask other applications to the machine. And to help you find some of those applications, I will present you a couple of drivers which you can use to find those. I will present them by discussing some case studies from the past. First case is one we did with Flyingcam, which are making radio-controlled helicopters for movies, for example. And in the middle of the helicopter, there is a part which was in the past an assembly of different parts, different materials. And by using a topology-optimized design, we only printed the structure which was needed. So this brings me to the first driver, which is material efficiency or lightweight structures. What if we can only use the material or print the material where we need it? Then we come to the next driver, which I will explain by using a case study of ASML. ASML is making lithography machines. And one of the parts which is used within this machine is the manifold you see on the left. The problem with this part was that the channels within the part were made by using drilling operations. And you can see that the corner within the channel is a 90-degree corner, which was resulting in quite some pressure jobs, which were causing vibrations within the machine. Now, by using additive manufacturing, they were able to optimize those channels. They didn't need to drill them anymore. They printed the channels. And by doing so, they were able to create a smooth transition within the channel. And as you can see in the middle, doing so, they managed to reduce the pressure drops within the part by factor 10. Another example is, for example, an injection mold. By using internal channels which are printed inside of the mold, we can have much more efficient cooling of the mold, which will result in a much faster injection molding process. So the big driver here is flow optimization. What if we can create complex channels inside our products? Then we come to the next driver, which I will explain with the case study of GE. Actually, GE tends to replace all their injection nozzles within the engines by additive manufactured parts. Why do they want to do so? Actually, on the left you see the conventional nozzle, which is an assembly of a lot of different parts. Every part in this assembly needs to be produced manually, finished manually, and later on assembled together by welding operations. Actually, by integrating all those parts within one part, they were able to have a much lighter part, to integrate 18 parts into one. And finally, the part is much more durable because there are no longer braces or welds inside of the part. So we have less maintenance and more flying. And the biggest driver for them to go to additive manufacturing was the integration of functions or the integration of different parts into one. And here the question is, what if we can add multiple functionalities within one part? Then we come to the last driver, which I will explain by a case study of RS Print. And actually RS Print is printing insoles, and those insoles are different from conventional insoles you can buy in the shop. Because they will start printing the insole based on a scan they take of your feet. So the insole will be very personalized and will be different for every customer, and they can also adapt it to all kinds of activities. Another example, for example, of customized parts are dental implants or other kind of implants. So actually, here the biggest driver is mass customization. What if we can start a series production where each part is slightly different than the others? And here you see a summary of those different drivers. Now, once we found an interesting case, it's important to start redesigning the part. Why is it important to have a good design? Because if you look at the cost of a metal AM part, we see that a lot of the cost is due to the manufacturing time, the material time, and the labor time. In fact, if we design the part with less material, we will reduce the printing time. And if we make a clever design, it will be often also more easy to post-machine it afterwards. And so we can reduce the labor cost a lot as well. Now, to help you during this design process, we defined a methodology to use or to take into account during designing a part. And it sounds like forget what you know, start from the function of the part, use as less material as possible, and any complexity you can add to the part is almost for free. Now, if we look at complexity, if we increase geometrical complexity with conventional technologies, which is the light blue line, you see that the cost often increase a lot as well. The same for the number of parts. If we have a small amount or a small series of parts, the cost of each part will most of the time be much higher than when we have a larger series. In fact, with additive manufacturing, it's different. So additive manufacturing is perfectly suited to have parts with a very high complexity in a very small quantity. Here you can see an example. So if we use selective laser melting and we design quite a conventional part with almost no complexity, or we design in the same bounding box a quite complex part, it will almost cost the same because we will use the same amount of material. A very important thing is, as you can see on those examples, we can create very complex designs, very complex parts, but we need to design them. So it's very important to be able to translate the desired design features into a cut geometry in rather an efficient time. Because if we need, for example, 10 or 20 days to design one part, the cost to print the part will be maybe cheap, but the cost to design it will be very high. So try to use the right tools to make the design of your part. Then another important thing to do is to forget what you know. And this is often one of the most difficult things to do because we are used to take into account drafts on the part as we do with injection molding. We think we can't use any undercuts on the part. With additive manufacturing, it's completely different. We don't need all those restrictions. Also, for example, a hole. Why is a hole round? Because we use a drill to make it. But with additive, we print it, so we can actually make any kind of shape, or we can give any kind of shape to this hole or the channel. If we look to the cost of producing a metal part, if we look back to the cost of producing a metal AM part, we see that a big amount of the cost is due to the manufacturing time. And in fact, there are a couple of ways to influence this printing time. We can play with the layer thickness. The thicker we make the layer, the faster we will print, but the rougher the surface will be. And this you can see at the picture, a part made with FDM in polymer. At the left top picture, you see a very high or a very thick layer. At the bottom right, you see a very thin layer. So the bottom will print much longer, but as you can see, the quality of the surface is much better. On the right, you see a comparison of the typical layer heights of different additive technologies. Now we can also increase influence the build time by changing the orientation of the part. If we would print the same part flat or vertical, the vertical part will take much more time with most technologies, because we will have to print much more layers than in the other direction. Now, on the other hand, this part orientation can also influence the mechanical properties of the part. So, for example, for snap fits, if we put them in the wrong direction, the mechanical properties of the part can be very bad and not what we would like to have. And actually, you can see it on the picture below. If we print the part horizontal, the layers will be in the good direction of the snap fit. If we print the part vertical and we push the snap fit, we risk that the part will break during the application. The part orientation can also influence the surface quality. For example, on the left, you can see an example of the staircase effect. We will often see this with selective laser sintering, one of the polymer printing technologies. And with the technologies where we need support structures, we see that after removing those support structures, the surface of where the support structures were attached will be also quite bad. Then we come to the third important thing to think about, and this is use as less material as possible. Why do we want to reduce the amount of material? Because of course it will reduce the weight of the part for the final application. We will speed up the process because we have to print less material. As you will see in the other video, the price of additive manufacturing materials are much higher than conventional materials, so we will increase the price a lot if we use too much material. Also, for example, for ecological aspects, and with some technologies, if we want to print very massive parts, it will be quite difficult. So by reducing the amount of material, we risk to have, or we reduce the risk to have geometrical deformations during printing. An example of this topology optimization process is this part. It's actually a gooseneck bracket project we did together with ASCO. On the left, you can see the design space we had in red, the non-design space we had in gray, and actually we applied all the fixations, all the load conditions onto this design envelope. Then we started a calculation, and on the right you can see the solution which was calculated by the computer and which we used to come up with a new design. So on the left you see the conventional part, which was made of stainless steel, which had a weight of about 2 kilograms. And by using this topology optimization process, we reduced the weight of the part by almost 600 grams. And then we come to the last point, which is to start from the function of the part. And I will explain this by a rather easy example. As you can see on the left, this was a part which was conventionally made out of a block of steel. And by using 134 drilling operations, they created a quite complex network of channels within this block. Now, this was quite complex to do, and actually by using additive manufacturing, we don't risk to have defects during the drilling operations, because we can just design the channels along each other, and then we only print the functional material, which is a certain thickness around the channel, and some material to fix the complete part within the assembly. And you can see a picture of the part on the right. Okay, so this was the presentation about design for AM. I hope you learned a lot of new things. If you have more questions, you can also always contact me by email or by phone. Thank you very much.